Sometimes we need to talk about independence of several events. And this issue is a little bit more complicated than independence of just two events. Let's look and see what can happen. Let's call events A1 through AN mutually independent. Or some people would just say independent. If our opinion about any one event AI does not change with knowledge of any combination of the other n-1 events. Let's look at the case n equals 3 first. So let's call the events A, B, and C. These are mutually independent if, so the condition turns out to be if the probability, well there's, let's say, two conditions. Probability of A, B, C equals, it factors as probabilities of each of the events individually. Let's call this triple-wise independent. And two, probability of A, B factors. So A and B are independent. A and C are independent. And B and C are independent. Let's call this pairwise independent. Now, a natural question to ask is, since we have two conditions here, would it be okay to just use the first condition, or would it be okay to just use the second condition? You might wish for that. But actually these two conditions are different. There are events that satisfy number 1 and not 2, and there's events that satisfy 2 and not 1. And each of these conditions is different than the combination of the two conditions. So we really do need both of them. Let's do some examples to see how we could satisfy one condition but not the other. So let's have events A, B, and C. Let's have these be discrete events, and I'll say how many elements are in each set here. 5, 4, 4, 3 make up A, and then a 6 and a 2 with the 4 and 4 make up B, and then there's no events in C. There's no elements in C that aren't already in A and B. So let's just do some easy computations. The probability of A is, let's see, 5 and 3 is 8, 4 and 4 is 8, so 16 over 16 and 8 is 24. Divide top and bottom by 8 and we get 2/3. The probability of B is 8 plus 8, 16 also, 16 out of 24, which is 2/3. And the probability of C is 7, 9 out of 24, divide top and bottom by 3, and we get 3/8. The probability of ABC is 4 over 24, which is 1/6. And if we multiply these probabilities together, probability of A, probability of B, probability of C, we get 2/3 times 2/3 times 3/8. 4 over 8 is 1/2. 3 and 3, so we get 1 over 2 times 3, or 1/6. So it turns out that probability of A, B, C does factor as probability of A, probability of C. They're both 1/2. But if we look at these events pairwise, probability of AB is, let's see, in the intersection AB we've got 8 out of 24, which is 1/3. Probability of AC is 7 out of 24. Probability of BC is 6 out of 24. But probability of A, probability of B is 2/3 times 2/3, which is 4/9, which is not the same as 1/3. Probability of A, probability of C is 2/3 times 3/8, which is 3/8, or 1/4, which is not the same as 7/24. And probability of B, probability of C equals 2/3 times 3/8. Again, 2/8, 1/4, which is not equal. Oh, this is equal to 6/24. So in that case, they ended up being the same. So I guess B and C are independent, but A and C are not, and A and B are not. To carry the calculations a little bit further, we see that, let's look at probability of A given B. We know we're in B, then it's 8 over 16, which is 1/2, which is different from the probability of A. Probability of A given C is, if we know we're in C, then it's 7/9. The probability of A given B and C, so if we're in B and C, the part of this that's in A is 4, so 4/6. And that actually is equal to the probability of A. So knowing B and C together doesn't change our opinion of A, but knowing just B changes our opinion of A from 2/3 to 1/2. Knowing just C changes our opinion of A from 2/3 to 7/9. So we can see that this triple-wise independence, the probability of A, B, C being equal to the product of the individual probabilities, doesn't quite capture our idea of our opinion about one event will never change with information about the other events. Because we can see our opinion of A does change with B, it does change with C. For some reason it doesn't change if we know both B and C, but our opinions do change given knowledge of some events here. And since B and C are independent, but A and B are not, and actually B and C are not. Oh wait, B and C are independent. A and B are not independent. A and C are not independent. So these three events fail to be pairwise independent, even though they're triple-wise independent. So now let's look at another example where the events are pairwise independent, but not triple-wise independent. All right, let's flip a coin twice. And let's define events. H1 is the first toss is a head. H2 is the second toss is a head. And E is the event that the number of heads is even. So we're flipping the coin twice. Apparently our sample space is head, 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 tail, tail, head, tail, tail. Those are all the things that could happen. So the probability of H1 is first toss is a head, well, 1/2. Probability of H2 is also 1/2. Probability of E, an even number of heads, so it's either 2 heads or 0 heads, 2 over 4, which of course is 1/2. Now the probability of H1 and H2 is, so this is the only possibility in the sample space where we have H1 and H2, 1 out of 4, which happens to be 1/2 times 1/2. Probability of H1E is, let's say we have an even number of heads on the first one, and the first toss is a head. Here are the two even possibilities, but only in HH does the first one a head. So that's 1/4, which happens to be equal to probability of H1, probability of E. And the probability of H2 and E is the probability that we have 2 heads and the second toss is a head. So that's again only this possibility, 1/4, which happens to be probability of H2 times probability of E. So it looks like these three events are pairwise independent, because if we take any two of them, the probability of the two events happening together is the product of the probabilities. All right, now how about the probability of H1, H2, E? So the first toss is a head and the second toss is a head, and we have an even number of heads. So that only happens in the first case. So that is 1/4, which unfortunately is not equal to the product of probability of H1, probability of H2, probability of E, which would be 1/2 times 1/2 times 1/2, which is 1/8. So we don't have triple-wise independence here, even though we do have pairwise independence. All right, now let's look at conditional probabilities a little bit. So since H1 and H2 are independent, we know that the probability of H1 given H2 is just probability of H1. Similarly for these two pairs of events. But what's the probability of H1 given H2 and E? So we want to be able to say that our opinion about any one event is not influenced by our knowledge of other events. Well, if we have H2 and E, an even number of heads, the second toss is a head, then we're in this first case, HH. But if that's where we are, then the probability that the first toss is a head is 1. That's the only possibility. That's 1, not equal to the probability of H1 alone, which is 1/2. Similarly, the probability of H2 given H1 and E is H1 and E says we have an even number of heads, first toss is a head. Has to be this. So given this information, the probability of H2 is 1. Again, not equal to 1/2. And the probability of E given H1 and H2 is, well, if we have head on the first toss, head on the second toss, then we certainly have an even number of heads. So that's also 1, not equal to 1/2. So even though we can say knowledge about one event doesn't change our opinion about one event, in this example, knowledge about two events does influence it changes our opinion about the third event. Alright, so for three events, to say that the three events are mutually independent, we need triple-wise independence and pairwise independence. What do we need for n events in general to be mutually independent? So n events A1 through AN are mutually independent, or we could just say independent, if for every k-element subset AI1 through AIK, so for every choice of k of these events, the subset is k tuple-wise independent. So that means for any collection of events here, the probability of those events happening is just the product of the probabilities. Now, often our assumption of mutual independence doesn't come from checking for every single subset that the probability of the subset of events is equal to the product of the probabilities. It comes from just often realizing that we're doing many trials of the same experiment, and one trial doesn't influence our knowledge about any trials, doesn't influence our opinion about other trials. So often the mutual independence assumption comes from performing multiple trials of the same experiment where we feel that knowledge about outcomes of trials don't influence our opinion about other trials. So that's a strong assumption, but if we were flipping the same coin many times, we might say that what happened on the first flip and the second flip and the seventh flip doesn't change our opinion about what's going to happen on the 12th flip, because we've inspected that coin, and no amount of further observation is going to change our opinion that we've got 1/2 heads, 1/2 tails. But it is sort of a strong This is a strong assumption. I'm not sure that in real life every instance of performing multiple trials really has this property. But let's look back at the Lehigh COVID problem and see how the independence assumption fits into those computations. So in a population with a 5% rate of COVID, you gather with 50 people. What is the probability that you've just come into contact with a COVID positive person? So let's define events E1 through E50 by E1 equals person I is healthy. So probability of EI is 95 over 100, or 19 out of 20. So the probability that you come into close contact with a COVID positive person is 1 minus the probability that you don't. 1 minus the probability that everyone is healthy. So 1 minus the probability of E1 through E50. Now, assuming that E1 through E50 are mutually independent, chosen at random from the population, this is 1 minus the probability of E1 times the probability of E2, etc., times the probability of E50, which is 1 minus 19 over 20 to the 50th, which we computed was 0.92. And actually, this is a much easier way to compute it than what we did, because we're just taking 19 20ths, 19 20ths, etc. 50 times, raise it to the 50th power, subtract from 1. Now let's look at why this is a strong assumption. So 50 people get together at a gathering. If none of them know each other, then sure, our opinion that one person has COVID is not influenced by our knowledge that somebody else has COVID. But if it's a social gathering, there's a chance that some people know each other. There's even, it's a strong possibility that some people live in the same apartment. So I think that independence at a social gathering would not be a good assumption. If we know that one person has COVID, I think our opinion that their housemate has COVID might increase. So I think that would lead to an even greater number here. But anyway, the assumption that these events are independent maybe is not exactly appropriate for this type of problem, even though it was very easy to compute the answer assuming that they're independent. We'll talk more about the appropriateness of independent identical trials in the future. The end.